Dear students, in this video we are going to study about mutual induction, coefficient of mutual induction, the unit of mutual induction between two long coaxial solenoids. Now let us study about the phenomenon of mutual induction. When an electric current passing through a coil changes with time, an EMF is induced in the neighboring coil, and this phenomenon is called as mutual induction. The EMF thus induced is called as mutually induced EMF. For this, let us consider two coils which are placed close to each other, and if an electric current I1 is sent through the coil 1, the magnetic field produced by it is also linked with the coil 2, which is as shown in the figure 4.21a, like this. If phi21 is the magnetic flux linked with each turn of the coil 2 of N2 turns due to the current in the coil 1, then the total flux linked with the coil 2, that is N2 phi21, is proportional to the current I1 in the coil 1. So this is shown in this diagram. These are two coils having N1 turns for this coil 1 and N2 turns for the coil 2. The flux linked with the second coil is given by phi21. The EMF is about E2. Whereas for this, there are two coils, coil 1 and coil 2, and the EMF is E1 for this coil N1 turns. And this is another coil having N2 turns, and if the current I2 is passing through this coil N2, coil 2, then there will be an EMF induced in this coil phi12. This E1 is the induced EMF, that is because of its magnetic flux, change in magnetic flux into the coil phi12. So here this N2 phi21 is directly proportional to the current I1, and N2 phi21 can be written as M21 I1, introducing this constant M21. So this M21 is given by N2 phi21 by I1. This is the constant of proportionality M21, that is called as the mutual inductance or coefficient of mutual induction of the coil 2 with respect to coil 1. And if the current passing through the coil is about 1 ampere, that is I1, then M21, that is the mutual induction, coefficient of mutual induction of the coil. M21, that is the mutual inductance of the coil with respect to first coil, that's given by N2 phi21. Therefore, the mutual inductance M21 is defined as the flux linkage with the coil 2 when 1 ampere current flows through a coil 1. When the current I1 changes with time, an EMF E2 is induced in the second coil. From Faraday's law of electromagnetic induction, this mutually induced EMF E2 is given by E2 equal to minus d by dt of N2 phi21. Thus given by minus d by dt of M21 I1. So the expression can be written as E2 equal to minus M21 d I1 by dt, that's the rate of change of current I1. And therefore the mutual inductance M21 is given by minus E2 by di by dt, where this di1 by dt is the rate of change of current I1 with respect to time. So here this negative sign in the above equation shows that the mutual induced EMF always opposes the change in current I1 with respect to time. And if the rate of change of current I1 with respect to time is about 1 ampere per second, then the mutual inductance of the second coil with respect to the first coil M21 is given by minus E2. So the mutual inductance M21 can also be defined as the opposing EMF induced in the second coil when the rate of change of current through the first coil is about 1 ampere per second. Similarly, if an electric current I2 through second coil changes with time, then EMF E1 is induced in the first coil. Therefore, the mutual inductance M12 is given by this expression N1 phi12 by I2, and therefore this can also be written as minus E1 by di2 by dt. So this di2 by dt is the rate of change of current I2 with respect to time, and where M12 is the mutual inductance of the first coil with respect to the second coil. It can be shown that for a given pair of coils, the mutual inductance is the same. That means M21 is also equal to M12 plus equal to M. So in general, the mutual induction between two coils depends on the size, shape, and the number of turns of the coils, the relative orientation and permeability of the medium. Now let us see what is the unit of mutual inductance. It is given by Henry and denoted by a letter H. So if the first coil, if the current passing through it is I1, then if it is equal to about 1 ampere, then N2521 will be equal to 1 Weber turns. Then the mutual inductance is given by M is equal to 1 Henry. Therefore, the mutual inductance between two neighboring coils is said to be 1 Henry if a current of 1 ampere in one coil produces unit flux linkage in the neighboring coil. And if the rate of change of current I1 with respect to time is given by 1 ampere per second, and the EMF induced is E2 is equal to minus 1 volt, then the coefficient of mutual induction is given by M is equal to 1 Henry. Therefore, the mutual inductance between the two neighboring coils is 1 Henry if a current changing at the rate of 1 ampere per second in one coil induces an opposing EMF of 1 volt in the neighboring coil. Next, we are going to study about the mutual inductance between two long coaxial solenoids. For this, let us consider two long coaxial solenoids of same length L. The length of these solenoids is large when compared to their radii, so that the magnetic field produced inside the solenoids is uniform and the fringing effect at the ends may be ignored. Let A1 and A2 be the area of cross section of the solenoids, with A1 being greater than A2, which is as shown in this diagram. So there are two coils of area of cross section A1 and A2. For the first coil, the area of cross section is greater, and the second coil has a less area of cross section. The turn density of these solenoids are given by N1 and N2. So for the first solenoid, the number of turns is about N1, and for the second coil, that is second solenoid, the number of turns is N2. And these two solenoids will share a common axis like this. So that is called as a coaxial solenoid. Let I1 be the current flowing through the solenoid, that is first solenoid. Then the magnetic field produced inside the first solenoid is given by the expression B1 equal to mu naught N1 I1. As the field lines of B1 are passing through the area bounded by the second solenoid, the magnetic flux is linked with each turn of the second solenoid due to current in the first solenoid, and that is given by the expression phi21 equal to integration of B1 dot dA that's equal to B1A2 as theta is equal to 0 degrees. Therefore, this can be written as mu naught N1 I1 into A2. The flux linkage with the solenoid, that is the second solenoid, is that is having a total number of turns N2 is given by this expression N2 phi21 equal to mu naught N1 N2 A2L into I1. And we know that this N2 phi21 is equal to M21 I1. So comparing the above equations, we can get the equation 4.13 as M21 equal to mu naught N1 N2 A2 times L. This gives the expression for the mutual inductance M21 of the solenoid, that is the second solenoid, with respect to the first solenoid. Similarly, we can find mutual inductance M12 of the first solenoid with respect to the second solenoid as given below. For this, let us consider the magnetic field produced by the second solenoid when it carries a current I2, that's given by B2 equal to mu naught N2 I2. So the magnetic field B2 is uniform inside the second solenoid, but outside the second solenoid it is almost 0. Therefore, for the first solenoid, the area of cross section A2 is the effective area over which the magnetic field B2 is present, and not the area A1. And the magnetic flux phi12 linked with each turn of its first solenoid due to the current in the second solenoid is given by this expression phi12 equal to integration of B2 dot dA. So B2 A2, that will be written as mu naught N2 I2 into A2. The flux linkage of the first solenoid with total turns N1 is given by this expression N1 512 is equal to N1L into mu naught N2 I2 into A2 as N1 equal to N1 times L. So N1 512 can be written as mu naught N1 N2 into A2 L times I2, and we already know that N1 512 is equal to M1 to I2. So comparing the above equations, we can write it as M12 as mu naught N1 to N2 into A2 L. So from these equations 4.13 and 4.14, we can write the expression for M12 that's equal to M21, so that's equal to M. So in general, the mutual inductance between two long coaxial solenoids is given by M equal to mu naught N1 N2 A2L. And if you are introducing a dielectric medium of relative permeability mu r inside the solenoids, then the mutual inductance can be written as M equal to mu naught N1 N2 A2L, because mu is given by mu naught into mu r.
Induction happens when a changing current flows in one coil. That changing magnetic field induces a voltage in a nearby coil. Think of coil A as the sender coil. Coil B is the receiver that gets the energy. Move or vary the current and B gets a push. That principle powers many everyday devices right now. Transformers step voltage up or down in the grid. Wireless chargers wirelessly charge your phone without any plugs. Induction cooktops heat pans very fast and efficiently. Guitar pickups turn string motion into electric sound. Simple magnetic teamwork. Small coils, big everyday impact.